In continuation to our lecture, now we will talk about case 2, which is over damping. Remember, that is the case where c square is greater than 4 mk, and if you see that roots lambda 1 and 2 is minus c plus minus under root c square minus 4 mk by 2m. So if c square is greater than 4 mk, then naturally this is positive, no complex part. Now you could see that both lambda 1 and lambda 2 will be negative. Is it clear or not? First term you see lambda 1 minus c plus minus under root c square minus 4 mk. The c square minus 4 mk, since mk they are positive, so this will be always less than c square, or this root c square minus 4 mk is always less than c. Obvious, because something has been extracted out of c square. If this was 0, they would have been equal. So naturally lambda 1 will be negative and lambda 2 also will be negative. This is the interesting point. Both lambda 1 and lambda 2 will be negative if c square is greater than 4 mk, no complex part. So it's a very win-win situation. There will be damping fast. Okay, that is why it's over damping. So if that is true, then x of t we can write as c1 e to the power lambda 1 t plus c2 e to the power lambda 2 t. Because lambda 1, lambda 2 are negative and they are distinct. So roots are distinct and negative. This is important. So what do you see here now? What is x of t? X of t was a perturbed quantity. So as time progresses, since lambda 1 and lambda 2 are negative, so naturally there will be decay. But will there be oscillation? No, there won't be any oscillation. So thus variation will be typically something like this. If it is x of t and time, it may vary something like this. It will come to the equilibrium, something like this. So see here, there won't be any oscillation. Lambda 1 negative, lambda 2 negative. So remember, this is again a mass spring damper system, but no oscillation. What is the trick? The message is, if you can select damping such a way, high damping, such a way that it is greater than 4 into mass into k stiffness constant, then there won't be any oscillation. So designer has the liberty. If he wants a over damped system, so he will select the C such a way, high value of C, such a way that disturbed quantity goes like this, perturbed quantities goes like this. That is very important. So this also demystify that mass spring damper system does not necessarily mean oscillatory system. Correct? And designer has so much of liberty, depending upon what sort of a response he wants, he has to select the value of C, M and K. Is it clear? Okay. Now, under damping over, over damping is just over. Now what comes to your mind? It's obvious. You will be more interested in the boundary between under damping and over damping. And that is our case 3. That is called critical damping. Before I come to this, let me take you back to the physical situation. What did we realize? We realized that you have to select the value of C, M and K to ensure or to get whatever you desire as an oscillatory response or a overdamped response. You have to select C, select mass, and select the value of stiffness. If I want to translate this to aircraft, C will be translated to CMQ, pitch damping derivatives. K will be CM alpha. What I am discussing is, we know that if I want to get a particular type of response, let's say we want to over-damped response, then C square should be very high compared to 4mk, or C should be very high compared to mk and this product. So if I translate this to aircraft, C means my pitch damping derivative, CMQ, and K means CM alpha, and M could be IY in longitudinal case. So that is how we are building a relationship between the understanding through mass spring damper system to aircraft longitudinal motion. That is why we are spending so much time on this. Now let us come to the critical damping case, case 3, where lambda 1, lambda 2 is minus C plus minus under root C square minus 4mk by 2m. For critical damping, you know that C square equal to 4mk. This is critical damping. And you could understand, if C square is less than 4mk, it is under damping. C square greater than 4mk, it is over damping. So C square equal to 4mk is the boundary which separates under damping and over damping. And this is also termed as critical damping. And you could see here, it has roots which are repetitive in nature, and they are minus C by 2m, and the solution for this roots for this differential equation, because it has a repetitive roots, so we'll write x of t as e to the power minus c by 2mt into c1 plus c2 into t. Carefully observe this. One can think of, as time is increasing, this may diverge, but see here, this is exponential. So this decay will be faster compared to the increase because of time. So this also will decay very fast. In fact, you'll see that this response is the fastest response among all the three. It takes shorter time to come back to the equilibrium. Okay. We'll see that. And it is also said that it is the fastest return of the system which is non-oscillatory. So what is the message? Message is, if damping C is less than C corresponding to this critical damping, then it will be under damped case. If C is more than this critical damping, it will be over damped case. And third thing, the fastest return of the system in a non-oscillatory mode if the damping C value is equal to the C critical. Okay. So this demands that we need to know a little bit of more on C critical, and we will try to understand what is this C critical means. We will also try to understand what is natural frequency of the system. Right. Remember, we defined omega d damped frequency as under root C square minus 4mk by 2m, and if C equal to 0, omega d is nothing but under root k by m. If I put C equal to 0, I can show that omega d is equal to this. And this is nothing but natural frequency. So when I talk about natural frequency, I am talking about a case when there is no damping. Clear? Right? Now, if I try to give a statement on natural frequency, which is here, natural frequency, I will define natural frequency is the frequency with which a system will oscillate if damping is 0. So whenever I think of natural frequency, keep back of your mind C is 0, no damping. Generally, there's a lot of confusion, and people will go on talking about damped frequency, but actually it's a natural frequency. Sometimes natural frequency talked about damped frequency. So whenever talking natural frequency, no damping. Okay, right? This should be clear to you. And damping ratio is another term will come. We'll see damping ratio. This is also a very important thing to understand. Let me erase this part. It is actually ratio of actual damping by critical damping. Denoted by zeta. Okay, actual damping by critical. You can see here, if this ratio zeta is more than 1, that means what? That means this system will behave like a over-damped case. Right? This will be over-damped. And no oscillation. If zeta is less than 1, that is damping, actual damping is less than critical damping, it's an under-damped case. Under-damped case, so there will be oscillation. And of course, it goes without saying, if zeta equal to 1, again there won't be any oscillation, and it will have a fastest return, no oscillation, and fastest return to equilibrium. So this is important. This ratio, damping ratio, has drawn a lot of importance, and that is why there's a need to understand this ratio and the meaning of this magnitude. Okay? So let us see, if I further go into this, I put actual damping is C, and critical damping, you know, it is 2 root of mk. Where from it has come? Because C square equal to 4 mk for critical damping. So C is equal to 2 root mk if I take the square root, and we have assumed that m, k, C all are positive. So that the ratio is C actual and the critical damping case. So this is nothing but zeta. Okay. Now let us see. We also know omega n is under root k by m. We'll do some trick. You'll see this will be useful. We may use another one lecture of 20-25 minutes talking about second order system at the most, then we'll dash into aircraft. But it is required that you understand these things. At least you might have done this thing long back. Okay? But try to understand and get the physics out of it. Okay? So C by 2 mk is zeta, and omega n equal to under root k by m. So if I now see m d square x by dt square plus c dx by dt, which is our equation of motion for a mass spring system, equal to f of t equal to 0 for free response. Please understand, I have used this term equation of motion. This, when I write m d square x by dt square plus c dx by dt plus k of x, it has come from that force balance, right? Newton's first law. So this is will be referred as the equation of motion. If I do that, then I can write this as m by k d square x by dt square plus c by k dx by dt plus x is equal to 0 for free response. And you also know m by k is nothing but 1 by omega n square. Then question comes, what is c by k? We want to know what is the value of c by k. Okay? And we'll use it c by 2 mk equal to zeta. And we know omega n equal to k by m, right? So we can easily see that C by 2 root mk is equal to C by 2 root, for m I write k by omega n square into k, because we know omega n equal to k by m. So for m it is, that expression I am using here, omega n equal to under root k by m. Let us not forget that. So this implies C is equal to, for this is, okay, this is nothing but zeta by definition. So if I manipulate this, I get C is equal to 2 zeta k by omega n. Okay? And what is our aim? Our aim is C by k. So C by k will be 2 zeta omega n. This is important. Right? So what we have got? M by k as 1 by omega n square and C by k as 2 zeta by omega n. Now I substitute it here to get the final equation. So what will happen? So if I substitute here, this equation will become d square x by dt square plus 2 zeta omega n dx by dt plus omega n square x is equal to 0. This is an equation of motion for free response using zeta and omega n. So this is equation of motion for what? For free response using zeta and omega n. And most of our analysis will be using this form. So what we are doing so far? Please understand. We realize one thing, that if we want to understand the dynamics of an airplane, we need to understand dynamics of mass spring damper system. Why? Because there is a stiffness type a parameter or attribute of an airplane which comes through Cm alpha, static stability. There is a damping type attribute which comes through pitch damping, Cmq. It also comes in the other plane also, like in lateral and directional also it comes. This is one. Second thing, we understood that for a mass spring damper system, depending upon the routes, depending on the selection of system variable, you can you can guide the response or transient. These are important because, after all, finally we will be studying all these dynamic stability to analyze the handling quality of the airplane. So we know that whether I want to design an over damped system, I want to design a critical damped system or an under damped system, or depending upon that, I can choose those variables, the system variables. Now to know more about it, in terms of mathematical modeling, we thought of converting this equation of motion into a form where you use damping ratio and natural frequency. These two are very important parameters when you try to evaluate handling qualities. And we define damping ratio as the ratio of actual damping to critical damping, and natural frequency as the frequency of oscillation when damping is 0. Most important part is, why from this sort of a form to this? Because we will see that zeta omega n and zeta into omega n, they will be exhaustively used to define the handling requirements, handling quality requirements. So whatever you understood here, although through mass spring damper system, we will have one more lecture on this, that's all, maybe 20-25 minutes. You will find once you master this, your understanding of dynamic stability becomes simpler. Those who go for a shortcut, they don't understand this, they try to understand the equation of motion of aircraft, they always complain, oh, highly mathematical, very complex. It is neither highly mathematical nor complex, it is a physics based, as long as you understand mass spring damper system. I am sure we will not commit that mistake, but not understanding this. Any problem, put up question in the forum. Thank you very much.